Hi folks, we're going to take a look at the process for sketching the graph of y equals ln x over x. Okay, and as you've seen me do before, I'm going to split this up into three main sections. Okay, and section 1 is going to be to determine everything I can just by the function itself. Okay, so first thing I'm going to consider is what's the domain of this function. So denominator can't be 0, but that's also included in the restriction for the numerator. Since it's ln x, we know that x has to be greater than 0. Okay, so we're only considering positive values of x. Okay, so next I'll look for my x-intercepts, which of course occur when the numerator is equal to 0. So ln x equals 0. Okay, and that occurs when x is equal to 1. Okay, so there's my single x-intercept, and it's the domain. It's in the domain, so it's fine. We're not going to consider a y-intercept since x equals 0 is not in the domain. Okay, let's go on to vertical asymptotes. Okay, and we definitely have a possible asymptote at x equals 0, so we're going to be approaching it only from the right since it's not defined to the left of 0. So we have to figure out what's going on at 0. So ln x is approaching negative infinity, okay, and I'm dividing by a number that's very, very close to 1. So think of a very negative number, say negative 1,000,000 divided by 0.001. That's only going to make it more negative. So this will still approach negative infinity. Okay, so not surprising there that we have a vertical asymptote. Okay, let's take a look at the sign of the function. Okay, so the only place, so we're only interested in greater than 0, and the only place that it could change sign is at 1. Okay, so the denominator is always positive. So to the left of 1, ln x is negative, and to the right of 1, it's positive. Okay, so we know the function is negative between 0 and 1, and positive for x greater than 1. Okay, and the last thing we'll do now is consider the end behavior. Okay. So the only thing we have to consider here is the limit as x approaches positive infinity, of course. Okay. Now this is where, again, we have to use that hierarchy of rate of growth. Now, by the way, in your future calculus courses, you will find a much more algebraic way of determining the end behavior here. But here we have to think that both of these approach positive infinity. ln x approaches positive infinity, x approaches positive infinity. So we consider that x approaches positive infinity more quickly than ln x does. So as x gets very, very large, it's the denominator that starts taking over. It gets larger much more quickly. So that means eventually this function will approach 0. Okay? So this is everything that we can get from the function itself. Okay, so let's move on to seeing what the derivative can give us. Okay, so first thing we'll have to do is find the first derivative. Okay, and make sure you do this very carefully. Don't make any mistakes because that'll sort of ruin the rest of the question. So here we have the derivative of the numerator, which is 1 over x, times the denominator function, minus the numerator, times the derivative of the denominator, which is just 1, all over the denominator squared. Okay, so here we have some nice simplification. Those reduce, so I'm just left with 1 minus ln x over x squared. Okay, so let's determine where the first derivative is equal to 0. So that's when the numerator is equal to 0. So when ln x is equal to 1. But of course, if we take the exponential function of both sides, okay, e to the ln x is just x, and so here we have x equals e to the 1. Okay, so this is our only critical point. Okay, so we have to determine whether this is going to be a maximum, a minimum, or neither. Okay, so here let's look at the sign of y prime. Again, we're only interested in numbers greater than 0. Okay, so let's look at e. So the denominator is always positive, so we don't have to worry about that. So here we have to consider, you can either stick something into your calculator or do it intuitively here. So if you think of ln x, okay, looks like this. Okay, so here if we take something less than e. So here when x is equal to e, y is equal to 1. So if I take something less than e, I get a number less than 1. So when I subtract, I get a positive number. Okay, and here if I take a number greater than e, I get something greater than 1. So when I do 1 minus something greater than 1, I get a negative number. Now if you're not comfortable doing it that way, hey, nice and easy. Just take your calculator, okay, and let's see what happens when I do 1 minus ln of something less than e is 2. There you go. We get a positive number. And then if I do 1 minus ln something greater than e, so 3, we get a negative number. Okay, so if you're not comfortable making these intuitive arguments, please make sure you're just testing numbers. Okay, so since we're going from increasing to decreasing, okay, that's what the positive and negative imply, that means we have a local max. Okay, and so we might as well get the point here. So we know it's at x equals e. And remember, to find the y value, you have to always go back to the original function. So ln e is just equal to 1 divided by e. So 1 over e. Okay, now when I'm actually putting this on a graph, okay, I'm going to want to approximate this here. Okay, so there's no way I can figure out exactly where e is on my graph. So here, what's 1 over e? 1 over e. If your calculator forces you to do this, to use the exponential base, just put exponent 1. Okay, and we've got 0.37. Okay, so there's our local max. Okay, so let's move on now to the second derivative, and that's going to be the third part of our process. Okay, so y double prime. So now I'm going back to this simplified expression. Okay, so the derivative of the numerator, well, that's just 0 minus derivative ln x is 1 over x. So we have negative 1 over x times the denominator function, which is x squared. Okay, and then minus the numerator function, 1 minus ln x, times the derivative of the denominator, which is 2x, all over the denominator squared. So this will be x to the 4th. Okay, so here, let's do as much simplifying as we can. So that's nice. We end up with negative x. And then here, let's distribute the 2x. Don't forget that there's a subtraction in front. So we've got minus 2x. And this is going to be plus 2x ln x. Okay, so just be very careful with the signs here. X to the 4th. So here, we can simplify. Negative x minus 2x is negative 3x. Plus 2x ln x, all over x to the 4th. Okay, and here we can factor out an x from both terms. Okay, so you have x. Here we have negative 3 plus 2 ln x, all over x to the 4th. And of course, we can simplify even more. Okay, so our final second derivative is negative 3 plus 2 ln x over x cubed. Okay, so let's look for our possible points of inflection. Okay, so that'll be when y double prime is equal to 0. So here the numerator needs to be equal to 0. So we have 2 ln x is equal to 3. So ln x is equal to 3 over 2. And take the exponential function base e of both sides. So x is equal to e to the 3 over 2. Okay, so let's test the sign of the second derivative to see if this is indeed a point of inflection or not, if the concavity changes. Okay, so again, remember, we're only interested greater than 0, so e to the 3 over 2. And this is where, again, I think this here I'll just approximate. Okay, so first of all, let's figure out what e to the 3 over 2 is approximately. So it's about 4.5. So I'll pick x equals 4 and x equals 5 to figure out where this is positive or negative. Now notice that the denominator, even though it's x cubed, remember we're only interested in positive x values, so we can not worry about the denominator. That's going to have to be positive. Okay, so let's look at the numerator. So here that was what about, so numerator is negative 3 plus 2 times ln of 4. Okay, and we see a negative number, so that means it's concave down between 0 and e to the 3 halves. And now let's stick in x equals 5, negative 3 plus 2 times ln of 5, and here we have a positive result, so that means it changes to concave up. Okay, so that means that we do have a point of inflection, okay, and that point is at e to the 3 halves. Okay, now remember, we have to take this number e to the 3 halves and put it back into the original function. Okay, so ln of e to the 3 halves is just 3 halves over e to the 3 halves. Okay, so keep that in mind as I write it down. So this is going to be just 3 over 2 over e to the 3 over 2. Okay, let's simplify that a little. So here we have e to the 3 over 2, and here 3 over 3 times e to the 3 over 2. Okay, but of course what we want to do is estimate this. Okay, so this was about 4.5. Okay, I'm not going to worry too much about being precise since I'm going to have to put this on a graph. Okay, and then here in terms of our denominator, we've got, oh, I just realized that should have been 2 from our denominator there. So here, what do we have? We have 3 divided by, okay, 2 times 4.5. That'll be precise enough. So it's about 0.33. Okay. So now we have all the information that we need to draw this graph. Okay, and of course, I'm going to do this by hand. Okay, you'll normally have a Cartesian plane to do this with, but let's see what we have to work with. So in terms of our x values, well, notice how I have to get to 4.5, 2.7, okay, and here my x-intercept of 1, okay. So that makes it a fairly easy x-intercept to work with. But when I look at my y values of the important points that I have to plot, I see 0.37, and here I see 0.33. So these are very small numbers. So when I'm drawing my graph, I'm going to choose the scale on my y-axis to be much smaller. Okay. So notice here, I'm not going to worry about negative x values. Okay, x and y. Okay, and so here we'll just go 1, 2, 3, 4, 5. That's as far as I need to go. Okay, and here what I'll do is, well, again, I have to go to 0.3, so I'm going to do 0.1, 0.2, 0.3, 0.4. Okay, so what are the important points? Okay, so we have our x-intercept was at 1. Okay. Okay. Next we have our local maximum, okay, which is going to be at 2.7, around there, 0.37. Okay, that's somewhere there. And then at 4.5, okay, I've got at 0.33. More or less there is my point of inflection. Okay, so I know that this is going to negative infinity here. Okay, so there's that part of the graph. Okay, I've got my maximum here, so I have to start going down. Okay, so still concave down, but at this point here, it has to become concave up. Okay, so not quite the nicest graph, but just to show that it is eventually approaching 0. Okay, but I've indicated that in my response. So here you might want to specify that this is my max and this is my point of inflection. Okay, so in this case here where it's maybe not, I didn't do such a great job here on showing concave up. Okay, but again, a little easier to do when you're working with a Cartesian grid. Okay, so let's just recap again. 3 steps. What can you do with the function? What can you get from the first derivative? What can you get from the second derivative? Okay, make sure you're being very careful in taking the derivatives, because one little mistake will bring everything down. Okay, make sure everything is justified. Okay, especially in terms of finding local extrema and points of inflection. Okay, and when you're actually setting these up to sketch on a graph, it's perfectly fine to estimate your points if they're not quite so nice. Okay, and that is it for a sketching example.